Okay, so it's good to see you, Benoit, and thank you for inviting me to give a talk. And one or two of the examples will perhaps also build on some of the things that Michael was saying earlier. So I'll try and draw some of those points. What I was aiming to do in this talk was to give a kind of overview of some of the things that can be done with time-resolved imaging, particularly looking at degradation and behavior of materials. Starting off in 2D, but then moving to 3D imaging, and maybe some of the results will inspire people to consider doing their own 2D and 3D imaging experiments. We have a big project with the ESRF in Grenoble just starting, and we also have the National Centre for Lab CT, as you mentioned at the beginning when you introduced me. And for those of you who are interested, the NXCT in the UK is a national research facility, so we have beam time to enable people to do lab-based imaging, particularly time-resolved imaging. And although mostly focused on research in the UK, we can also consider projects with people from outside of the UK. So I thought, as I said, I'd just give a very short introduction to 2D imaging and the correlation of 2D images, and seeing the results that Michael was showing, looking at cracking in coatings. The technique I'm going to show is quite applicable to that too. This is digital image correlation. It's now very heavily used. We started doing digital image correlation in the 1990s, but now the resolutions that you can achieve are really outstanding. Here we're looking at hot creep. So we have a lab in a microscope. We can undertake mechanical and thermal tests over many days inside the scanning electron microscope. And here we're looking at the creep deformation of magnesium alloys. And you can see the magnesium AZ31 microstructure at the top. And you can see what we do is we place a gold, well, we remodel a gold particle pattern on the surface, a very fine pattern. You can see this is a 1 micron square here. So we coat the surface and remodel the gold to form these very fine particles, and then we can, when we strain the sample, we can use these particles to measure and quantify the strain fields. And you can see an example here for this magnesium here at room temperature. You can see as we increase the strain, and what I'm showing here is the accumulated strain. And so, for example, in the bottom left-hand corner, you can see some twins. Twins there, and you can see deformation, a number of slip planes, and you can see some interaction with the grain boundaries. So this is now very well established high resolution technique. We can image samples. This one is about this field of view is about 40 microns by maybe 100 microns, so quite a 150 microns perhaps, so quite a small area and high resolution. And I wanted to show you just one example from that, and that's what we've been doing looking at AZ31. So we carried out a number of experiments. I'm going to show you just two. One looking at the deformation at room temperature, and then one looking at the deformation at 200 degrees centigrade. At room temperature, what I'm showing here is the differential strain. So this is the strain between successive images. And what you can see, if you look carefully, you'll be able to see, for example, how certain slip bands. So, for example, you can see for twins here, you can see some twins. And what happens is you get a twin in the center, and then that twin extends laterally. So if you watch, you should see those bands move laterally as straining goes forward. So here you can see strain both located, concentrated at grain boundaries. You can see twinning, and you can see general slip. But if we now move to high temperature, you see a very different picture. So here we can see the differential slip, in other words, the slip between each successive image. We can see strain mostly accommodated around the grain boundaries. You see very little strain internally within the grains, but you can see highlighted by the bright yellow color, which is 0.5 effective strain. You can see very severe strain around the grain boundaries. You can also see some rather interesting effects as these grain boundaries move. And you'll see, for example, if you look at the right-hand square, you should see there, can you, whoops, sorry, I've just incompetence. You'll see those the grain boundaries pinch off here. And And similarly in this grain, you'll see the grain boundaries pinch off here. Here it comes. I think, there we go. And a new grain is formed. So we can understand how grains are sliding. Well, one might call it sliding. It's really a very localized deformation local to the grain boundaries. We can see lateral movement of the grain boundaries during creep, and the creep rate here is about 10⁻⁶. So this experiment took many days inside the electron microscope, and we were able to acquire images continuously throughout, and then to acquire EBSD at the beginning and EBSD at the end. The strains, as you can see from the original picture, the total strain, if I go backwards, sorry, there we are. The total strain at 250 is about 45%, 50%. So quite large strains we're looking at in these systems. Okay, so my point there really was also that you could use this to pick up the cracks that Michael was showing in the last talk. The DIC digital image correlation is very successful at picking up cracking in coatings. You can see the concentrate, you can see the changes in the strain where the cracks are forming. So that can be another way of monitoring cracking at high temperature remotely. I'm going to look mainly though at X-ray CT. So computed tomography, as you probably know, involves an X-ray source to create a radiograph, and then you rotate the sample and you take up to 3,000 or 4,000 radiographs, sometimes as little as a few hundred, but you take many projections, and from those projections you put together a 3D picture. So here's the kind of radiographs, and the three-dimensional image is shown underneath. And of course, because the method is non-destructive, you can undertake many scans one after another, and so you can do time-resolved imaging. One of the problems is the resolution is about 1,000th of the volume, or at least the dimension that you're scanning. So if you're scanning a sample that's 1 millimeter across, then your resolution could be up to a micron. But if you're imaging, if you want to image an area of say 10 millimeters, then probably the best resolution you can do is 10 microns. The penetration can be controlled by the accelerating voltage. The higher the energy, the higher the penetration. And so we tend to do scanning on very large objects at very hard energies, and we tend to do scanning on very small objects using softer energies, because we want to get enough contrast to see the object, but we also want to get enough penetration. So I'm going to start by looking at high frame rates, where you want to record 3D images in real time to capture fast phenomena. And here this is a graph we produced about 6 or 7 years ago now, and it shows how, as you increase the resolution, the time to acquire a scan goes up. So very high resolution, so for example, if you want to image at 0.1 microns, then it might take you hundreds of seconds to acquire enough flux on the sample to acquire enough photons to create an image. So if we look, you can see that the high speed imaging is done at synchrotrons, and the lower speed and lower frame rates tend to be done in the lab. But nevertheless, even in the lab, at 10 microns, you can acquire images in minutes. Of course, this was produced 7 years ago. These curves are moving towards the bottom left corner as we get better sources, and as we get better detectors, and as we get better reconstruction algorithms, so we can deal with more noisy data. But I mean, the simple message is, if you want to get high resolution at short time scales, then you need to use a synchrotron with the higher flux that a synchrotron, a large-scale facility, provides. Here's an example of what we can do. And again, this will be 2D imaging. It will be radiography. But here we're looking at how you can process materials in additive manufacturing by using a laser beam to melt the powder. And we can scan the laser across the sample. And at the same time, we can acquire the radiographs as we scan the laser across. And I want to show some images. Here you can see a radiograph. So this is a a through material image, and you can see quite clearly the powder here. You can see the molten metal. You can see the boundary between the molten metal and the powder, and the laser is moving from right to left across this image. And what you can see over many hundreds of milliseconds, you can see the molten metal, you can see the powder moving, you can see material being lost, you can see entrained defects. You can see, if you look carefully, you can see entrained bubbles that will then end up in the final piece. So this has helped us to understand how to control laser processing to get better samples with fewer defects. And I'll come back to those defects later. But again, in this case, you can see that if you get it wrong, then the melting becomes discontinuous. If you have the energy too low or the scan speed too quickly, you don't get proper melting. Okay. Another example of what you can do at high speeds was done at the ESRF, and this is looking at, and we've done similar experiments at the Paul Scherrer Institute in Switzerland, where we're looking at the collapse of carbon fibers. So here we have a unidirectional carbon fiber composite, and you can see in the famous INSA rig, in fact, this was provided by our colleagues by Eric Mayer at INSA, and you can see the little rig with the sample in. So we have a little carbon fiber unidirectional sample, and you can see that what happens is you get kinking. So what we'll see is we've put a little notch on the right hand side, and as we compress this sample, you'll see the formation of a collapse zone. This is being recorded at 20,000 frames per second. See, one thing it's very clear is that the kink occurs over just a few frames, so over just a few microseconds, and so we get this should say 50 microseconds, not 50 milliseconds. So it's 50 microseconds per projection. So you can see that the kink band forms very, very quickly over just a few hundred microseconds, and you can see the broken fibers and the displaced fibers. What we are now doing is using imaging to measure the bending of the fibers just prior to the propagation of this kink. But you can see already here, you can see that the fibers have all bent quite heavily out of plane, and you can see that the cracks are starting to form. You can see cracks where the fibers have broken. And of course, we can then do 3D imaging. This is 3D imaging, but much slower rates. This was done in the lab, and you can see those kink bands very clearly. You can see matrix microcracking because of the matrix plasticity as the fibers kink. And in fact, matrix plasticity is very important in terms of understanding and controlling kink. And you can see a number of other features related to the fracture of these fibers, and you can then correlate that to electron microscopy images of the failed sample. We've also done a lot of work looking at growth of defects in steels, and this is SA508 steel. And you can see that when you look at the fracture surface in SA508 steel under tension, it comprises a number of really large and deep ductile dimples, and many really tiny ones, many tiny dimples. And at the bottom of each dimple, you find a cementite particle, and at the bottom of each large particle, you find a large inclusion. And when we do X-ray imaging, you can see those very long voids, and you can see a cloud of very fine voids. And we wanted to study these in real time. So again, we were able to do a fast acquisition. Here we're doing 3D imaging, and you'll be able to see as straining proceeds, you'll see the void, which is in gray, forming around the red inclusion. And you can see the void becomes incredibly elongated as straining proceeds. So the blue shows the tensile curve, the red shows the size of the inclusion. And if I just repeat that, you'll see the growth and extension of that void. But the void doesn't extend very far laterally. It extends longitudinally, but not laterally. And so that's why we get these very deep voids on the fracture surface. If we look, in addition, we get the nucleation of very, very small voids, much, much smaller voids, but many hundreds of them. And these nucleate from the semen-type particles. And it's actually the nucleation and growth of these very fine defects that ultimately gives rise to failure as they start to link up. And you can see the blue shows the linking here of these very, very fine defects. So it's not the large defects that cause the problem. In this case, it's the link up of these very, very fine semen-type related defects. Right, now, again, because of the focus of the talk, I thought it would be good to look at some corrosion experiments. So here we have experiments we've been doing with Brian Connolly. And here, this is using in situ experiments to measure the growth of corrosion films. And just as Michael was talking about the stability of corrosion films, we're very, very interested in the stability of corrosion films. And here you can see the setup. We're in real time, we're rotating the sample, acquiring the images, and then rotating it back, acquiring images, rotating, rotating, rotating. When we go at very high speed, the sample just keeps rotating round and round. But in this particular case, you can see that we're rotating backwards and forwards. So the wires and the wires don't become tangled and wrap around the sample. You can see in this case, we can control the environment. We can have flow in through the bottom and flow out through the top of our cell. And we can watch the growth of corrosion films in real time. In this case, at 80 degrees C in CO2 saturated solutions. And of course, that allows us to build up some quite detailed pictures of the growth of these films. We can understand the interconnected porosity, which is shown here in blue. We can also understand a little bit about the crystalline state of the corrosion film. So if I just show this image here, you can see the growth of the film over first at 3 days and secondly after 6 days. And we can see that we start with essentially start with a mixture of siderite and chicanovite, but we grow these large crystals, and these large crystals of siderite can be followed and monitored. And here we can see the yellow. We've segmented the siderite in yellow, and you can see we can understand how porosity is also critical. So if you look on the right-hand image here, you can see porosity between the big crystals and the basic corrosion film. So we can understand how the crystallites grow. We can understand the porosity that's critical to continuing the corrosion process and the interconnectedness of that, and we can understand that as a function of conditions. If we want to go to longer timescales, then it's often better to do work in the lab. In the lab, we have obviously the opportunity at a large scale facility, an experiment might last 2 or 3 days. At the extreme, it might last a week. But in the lab, we can do very long timescale experiments. So in this case, our fluxes are much lower, but we can still get really good resolutions. We can get resolutions well below a micron, in fact, down to 50 nanometers in extreme cases. So we have a system that will take us down to 50 nanometers. Just to give you an example of a long time experiment, this shows the oxidation of a boiler tube. And this is a nuclear boiler tube running at 550 degrees centigrade. And here we can see that we've taken the sample and observed it after many hundreds and thousands of hours. And we can see the growth of the oxide on the film, on the fins of the cooling fins over a period of time. And we can understand the kinetics of that process. I'll just show that again. We can also look at oxidation and corrosion below films. So in this case, we have a thermal barrier coating. So this is an aerospace application where we have a substrate, we have a thermal barrier coating, and we have a thermally grown oxide. And you can see over time from 0 to 20 to 120 hours, you can see how the thermally grown oxide is forming at the joint between the thermal barrier coating and the metal substrate. And we can also see how certain kinds of defects are starting to form at that interface. And so we can start to understand just as some parts of that diagram that Michael was showing in the last talk, where we were talking about different conditions for failures. Well, here we can see, we can understand why coatings defects occur at the interface between the coating and the substrate, and these defects can lead ultimately to spalling of the coating. And I wanted to go back to those defects that we studied right at the beginning. So in the radiography, we were able to study the inclusion of defects, voids in the additive manufacturing. And here we're looking at an additively manufactured material. And what you tend to find is two types of defects. We find round pores that are entrained gases. They tend to be rather circular in their shape and relatively small. And then we have more pancake-shaped, flatter, more angular defects. And those defects tend to occur due to lack of fusion. So these lack of fusion defects are, on the whole, somewhat larger. They, as I say, they tend to lie flat relative to the build direction. So in this case, the build direction is vertical, and you can see these red defects tend to lie somewhat normal to the build direction. So it's very important to understand how to manage and mitigate these large defects. And one way that has been proposed is that subsequent to manufacturing, you use hot isostatic pressing as a way of closing these voids up. And we can use X-ray imaging to actually determine the efficacy of that. So here we can see a sample of additively manufactured material, and we can see the defects rendered in red, but we can see both the fine gas porosity and the larger loss of lack of fusion defects. And what we find is that when we hot isostatically press this sample, we can remove, or at least eliminate what looks like eliminate the majority of those defects. So we can optimize that hipping process to minimize the defects using X-ray imaging to confirm that. But what we find is that after heat treatment, those defects start to reoccur. And we know that these are the original defects because when we look in the when we correlate the as-built images with the same location immediately after hipping, we can see that these pores have largely been closed up. But what we can see is that after heat treatment, a pore has reopened at that location. So we haven't successfully closed up that pore. We simply brought the faces into contact, and the gas pressures cause them to reopen upon subsequent heat treatment. So one has to be very careful when applying hipping as a means of mitigating these defects. The other aspect where time-based imaging can be really useful is not just in following the manufacturing process, but actually following the fracture and fatigue process. So here we're looking at fatigue crack initiation from these samples. And you can see here on the left-hand side, one of these defects one of the defects located at the surface has caused the growth of a fatigue crack from that location. Sometimes they lie subsurface, as you can see over here, but often very close to the surface. And so we find that defects on the interior tend not to be that important, but defects either at or very close to the surface tend to be critical in terms of the fatigue behavior of this material. And what we can do is we can use time-lapse X-ray imaging so that we can fatigue the sample, and we can watch as we get more and more fatigue cycles. So what we have here is we have the red shows the defects, and this time we're looking in transmission, and we're as if we're looking down through the sample. And as we look down through the sample, we can see a number of voids. Some are rather large ones internally, and we also have a number near the surface. And what you can see here is when we actually fatigue this sample, if we measure the growth of these cracks every 10,000 cycles, we get contours so we can see the growth of the defect initiated crack. And you can see here there's a small, in A, there's a small defect near the surface, And you can see that after a certain number of cycles, that's caused a crack to propagate as a sort of half-penny crack, and we can follow the growth of that defect. Occasionally, we'll get growth from an interior crack, an interior defect. And here we can see really quite a large interior defect. And you can see that the crack has started to grow from that large defect. But on the whole, it was much more common to see, as in C and A, defects growing from the surface or the near surface region. But this enables us to establish a better understanding of the fatigue performance and to produce a probabilistic approach to understanding how many cycles to failure. So if we look at the fatigue curves for that data, here we can see a large scatter. So if we look at the stress range versus the number of cycles to failure, we can see that as we increase the stress, we get fewer and fewer cycles to failure. But what you can see is a very large scatter from sample to sample. But if we were to use X-ray imaging to see the defect sizes, what we find is that if we look at different size defects, you can see that the samples with the best fatigue performance tend to have the smaller defects. So what we've done here is take that data that we saw and plot on what the critical defects, the size of the critical defects, and we can see that for the larger critical defects, we get the shorter lives, and for the smaller defects, we tend to get the longer lives. What we can also see is that for larger critical defects that form internal defects, and this is an internal defect, we can see that again, we get a longer life. So this is helping us to understand the effect of different types of defect, different locations of defect, and it enables us to build a probabilistic approach to fatigue lifing of additively manufactured components. So I've given you a rather quick overview of some of the opportunities and some of the insight that can be gained from 2D and 3D imaging. X-ray CT is particularly invaluable for 3D imaging because, as a non-destructive technique, it provides us the ability to follow the behavior of materials, either in processing, as we saw with the additive manufacturing, or during life and during failure, as we saw with the composite materials and the fatigue cracking and so forth, and with the corrosion. So it enables us to understand evolution of a single sample and to follow it through life. What we can also do is we can correlate that with post-mortem high-resolution electron microscopy or chemical analysis, because we can locate regions of interest. We can excise them using a plasma fib or a laser beam, and then do high-resolution electron microscopy of those regions of interest to look at the local chemistry, to look at the local crystallography, or to look at the local phases. By correlating in 2D, we can do digital image correlation to measure the strain, and that can be useful for coatings. It can be useful for understanding polycrystalline behavior. And we can also, if we have internal markers, and in some cases we can have internal markers that we can be detected by X-ray imaging, we can use digital volume correlation. And there's a number of groups who've done a lot of work looking at cracking, where they've used internal markers to measure the strain internally by digital volume correlation. We need to increase the energy as we look at larger and larger parts. So the work we did, for example, on the boiler, on the cooling fins, in the nuclear application, we use very hard X-rays up to 300 kV, whereas the work we did on small samples of carbon fiber, we were looking at energies of 20 to 30 kV rather than 300, so that we get better contrast on small samples. Generally, synchrotrons are best for small samples because largely they illuminate only a small region, usually millimeter sized. So synchrotrons are generally best suited for millimeter sized samples with micron style resolutions with timescales of seconds or even sub-seconds to minutes. Whereas laboratory CT tends to examine larger samples. It's very well suited to samples of centimeters or larger sizes, and can image over timescales running from tens of minutes to many days or even to years. It is possible to do micron scale or submicron scale imaging in the CT in the lab, but the timescales tend to be longer. And as I said, frame speeds up to about 50,000 frames per second are accessible at synchrotron sources. So there really are, you can really look at the dynamics of a whole range of behaviors. Okay, I hope that's given you some inspiration and some ideas about potential experiments. I think the future is very bright, both for X-ray at synchrotrons and X-ray imaging at laboratory sources in combination with electron microscopy. Thank you for listening.